Hi everyone, in this video we're going to learn about what are called relative extrema or extrema, however you want to pronounce that. And that is maximums and minimums. So for example, if you look at this graph below, which is the population of the state of Kentucky beginning in 1981 and ending in 1990, you will see that in 1981 there was a minimum. In, 1982, 83, there was a maximum. Somewhere in 1988 or 89, there was a minimum. And then again in 1990, there was a maximum. What we're interested in are what are called relative maximums and minimums. So basically those are high points and low points in the graph, but not necessarily the highest points and the lowest points in the graph. So to be clear, let's label some of these. These points right here and here are called relative minimums or minima. One of them turns out to be an absolute minimum. So that is an absolute minimum, which we will talk more about in the next section. And then we also have two relative maximums. Relative maximums. One of which is an absolute maximum. So you might notice something about these relative maximums and minimums. They either occur where the slope of the tangent line is 0, so p prime of x is equal to 0, p prime of x is equal to 0, or they occur at an endpoint. We're going to focus our attention on where the derivative, the slope of the tangent line, the rate of change, is equal to 0. So a little bit of vocabulary here. Critical points of a continuous function are points, we're going to call them x-coordinate c, y-coordinate f of c, at which f is not differentiable or the derivative is 0. So f prime of c is equal to 0. Not differentiable would be an example where we have a corner, so maybe a function is cruising along like this and then has a corner. This would be a critical point even though the derivative is not equal to 0. So let's take a look at a simple example. We have the function f of x is equal to 0.4x squared minus 2x plus 10. And as you know, that's a quadratic, so it's a parabola that opens up. It has a slope function, aka derivative, that is 0.8x minus 2. If we set that equal to 0 and solve for x, what we find is x is equal to 2.5. So what we know there is that f of x has a relative minimum, and we know it's a relative minimum because we know it's a parabola that opens up. So basically what we're saying here is at this x value, f prime of x is equal to 0, and this x value occurs at 2.5. Well, that allows us to find f of 2.5, plug that x value back into the original function, and it turns out to be 7.5. So we can say that that function, f of x, has a relative minimum of 7.5 at x equal 2.5. So let's take that idea and apply that to our population of Kentucky problem. So here's the function p of x for the population of Kentucky from 1981 through the end of 1990. and x is the number of years since 1980. So x equal 1 would be 1981, and so on and so forth. So first part, part A, it says write the derivative of p. So if we were going to write the derivative of p, we would take 3 times 0.395, and if you verify that, you will see p prime of x is equal to 3 times 0.395 is 1.185. X to the second power, we reduce the exponent by 1, minus 2 times 6.67, which is 13.34, x plus 30.3. Locate, in part B, we're asked to locate the inputs at which p has a slope of 0. So effectively, what we want to find is where p prime of x is equal to 0. And we are going to use Desmos to do that for us. So I am going to jump over to Desmos, and I already have that function p prime of x entered, and you can see that I've entered it as y is equal to the derivative of p of x, and you can see it's parabola, and you can also see that it has locations where it is 0 at 3.156 and 8.101. So at those places, I know that the derivative of p of x is 0, which means that p of x has a slope or a rate of change of 0. So we're going to jump back over here. In part C, it says calculate the population at the critical points. So p of 3.156, and you can verify this on your own, but it's approximately equal to 3,703, and p of 8.101 is approximately equal to 3,679. Now we want to interpret those. So for the first one, during 3.156, that'd be 3 years after 1980. So during 1983, Kentucky had a relative maximum in population of 3,703,000 people, because that function was in thousands of people. Now you might be asking how I would know that it's a relative maximum. So if you think about the graph that we were given earlier, it kind of went like this and then like that. So I know that this relative maximum occurred right there at an x value of 3.156. The better way to think about that, without having to think about the shape of the population function, is thinking about the fact that the derivative went from positive slope to negative slope. Now, how would you know that? If you were to actually go back and look at Desmos, at an x value of 3.156, to the left of it, when x is less than 3.156, the derivative is positive, which means the population is increasing. To the right of it, of 3.156, the derivative is negative, which means the population is decreasing. So if the population went from increasing to decreasing, we have to have a relative maximum. Similarly, at the x value of 8.101, the derivative of the population goes from negative to positive, so that means the population function is going from decreasing to increasing, which gives us a relative minimum. So this location right here at x equal 8.101, we know we have a relative minimum. So during 1988, Kentucky had a relative minimum in population of 3,679,000 people. Again, the derivative is 0 there, but the derivative was changing from negative to positive. We moved from left to right. We're going to talk more about whether or not those are absolute maximums or minimums in the next section. So we're going to finish up with one more example, relating zeros of a derivative to relative extrema of a function. So here's a function about sleeping habits. The percentage of people in the United States age 15 and older who are sleeping at a given time of night can be modeled by this quadratic function, where t is the number of hours after 9 p.m. t applies from 0 to 11 p.m. Notice that it does include the endpoints of 0 and 11, which will be relevant in the next section. Locate any critical input values of s on the interval from 0 to 11 and calculate the output value for any critical inputs. So s prime of t is the first thing we're going to find, and that is negative 2.63 times 2 is negative 5.26 t plus 29.52. We are going to set that equal to 0. If you set that equal to 0 and solve, we do not need Desmos for this. We're going to get negative 29.52 over negative 5.26. If we use our calculators there, we get t is approximately equal to 5.61. So what I know is that s of t is 0 at t equal 5.61. What I don't know without thinking about it or looking at the graph of s prime of t is t equal 5.61, the location of a relative max or min. If you were to graph s prime of t, what you would find is you would have a line that has a negative slope. So s prime of t would look like this. This would be t equal 5.61, and you could see that the derivative goes from positive to negative there. So we have a relative maximum because the function s of t goes from increasing to decreasing. Another way you could figure that out from this particular function is s of t is a quadratic that opens down. So at 5.61, t equal 5.61, we have a relative maximum there. So s of 5.61, you can verify this with your calculator, is approximately 96.36. So our interpretation of that would be the percentage of people in the U.S. 15 and older that are sleeping at t equal 5.61 hours after 9 p.m. is approximately 96.36%. And again, you can verify by looking at the graph of s of t that we have a relative maximum there, and s prime of t, the derivative goes from positive to negative, so that tells us that s of t is going from increasing to decreasing, so we know we have a relative maximum there. In part C, it says, interpret the point marked on the graph of s. In part B, this point right here is the relative maximum in the percentage of people sleeping at the time 5.61 hours after 9 p.m.